In our next section, we're going to talk about the BGP best path selection process and talk about specifically how the order of the selection process works, and then what are the different ways that we can manipulate the best path selection. And then in later sections, we'll look at specific configuration examples of how we actually implement these differently with different attributes like local preference versus wait, or AS path versus med, and so on. Now again, the path selection is a very key important point to BGP, so I would highly recommend that you memorize the path selection. And the reason why is that the document that you would normally reference in a real design for this is not available during the exam. So ultimately what the best path selection is going to control is which route goes to the routing table from the BGP table and then ultimately can be advertised to other peers. Now the path selection in general is standardized. It's in the rsv5 BGP version 4. Specifically, you can see the link there. It's under section 9.1 under the decision process. But we're looking at it from Cisco's implementation point of view, so we need to look at once they get into the tiebreakers or once they get into the really nitty-gritty details of selection, exactly what happens. So this document here again, BGP best path selection algorithm, is the one that you generally want to reference. So I would recommend to bookmark this and make sure that you read through this a bunch of times. Now the first thing we need to think about in the path selection is what are the prerequisites. First and foremost, we have to have a route to the next hop in the routing table. And we talked about the reason for this over and over and over, that BGP is not a routing protocol. It is a reachability protocol that uses other protocols to provide transport. So this means that when BGP presents you the prefix, it presents you the length and the next hop. It's up to IGP to figure out how do I actually do route recursion towards that next hop. So if the route recursion process fails, BGP cannot use the route, so it just skips over path selection and it cannot advertise the prefix. So again, when we're looking at this from the actual CLI point of view and we look at the show IP BGP, the key field that you're looking for here is the greater than sign in the status code. The greater than sign means that this is the best path. This is the one that can ultimately get installed into the routing table and then can get advertised to other peers. Next, we have the legacy synchronization rule, and I'm not really going to spend a ton of time on this because there's not really a practical use case for it anymore. But the original problem was that the routers in the core of the network weren't strong enough to run BGP. They didn't have enough memory, they didn't have enough CPU. In today's networks, that's not really the case. The memory and CPU is not really the limiting factor of the router, but originally it was. So the solution they came up with was to say, well, they can't run BGP, or maybe the code doesn't even support it, so let's just redistribute BGP into IGP at the edge. So then when you're learning a route from an iBGP neighbor, we would need to synchronize it with the IGP table in order to make sure that we can actually provide transport for it. So the idea is that if you were forwarding packets over someone that wasn't running BGP, they would drop the traffic unless they had an IGP route to it. So that's what the synchronization rule says, is that for every iBGP learned route, you have to have a matching IGP route, but in newer code, it's off by default. So you may want to turn this on and just see what the result is if you see synchronization under the BGP process, but beyond that, I'm not really going to go into the details for it because it's a legacy rule. Okay, next we then have to make sure that the AS path does not contain the local AS, which is the normal eBGP loop prevention. Now we can disable this if we issue the allow AS in command, which affects the filter inbound, or we'll see later when we're doing MPLS L3 VPN, we can do the AS override feature on the provider side outbound towards the customer. But under normal cases, unless we're doing allow AS in or AS override, anytime your own autonomous system is in the path, BGP is going to throw the prefix away. And again, you can see that why is the route being filtered when you look at the debug IPBGP updates. So it'll simply tell you that RAS is in the path, the route is looped, so it cannot be installed in the BGP rib, cannot be used for best path selection. The other one is that normally you would check the first autonomous system number in the path to make sure that it is actually the neighbor's ASN. What this is preventing against is some sort of injection attack against BGP, that if maybe the session is unauthenticated and someone is able to guess the sequence numbers, they could spoof the session and send you a bunch of updates with random AS path information. So normally you're going to do this, you would have BGP Enforce AS configured, and it says just check the route as it comes in. If I'm peering with AS 200, logically the first number in the path should be 200. So it's a very basic check, but up at the application level of BGP to make sure that the path is actually valid. Okay, now we get into the actual path selection order. So once we've met the prerequisites, now we start to go through the decision process. The first one is going to be the pre-best path community, which we'll talk about this later, but it's basically a mechanism that allows you to trump the regular decision process by doing some other modifications. So we will talk about this in more detail, but under normal circumstances, when you don't have pre-best path community, then we're going to look at the weight first. Now, the thing to remember about the weight is that this is only a locally significant value. So if I select a path based on how I weight the prefix, it doesn't mean that you're necessarily going to choose that same type of decision. Also, this is a Cisco proprietary feature. So other vendors do have similar things to it, but the point being is that it's not advertised. So it's locally significant to the process. When I make the change, it doesn't affect you. Now, in most cases, you probably don't want to do that. So it's more common that you would use the local preference. Local preference in general is the standardized way on the internet in order to select a path outbound. So a higher value is going to be preferred. It's not advertised to eBGP peers, but we'll see that there's a trick with community signaling we can use in order to send certain communities to an eBGP peer in order to have them affect the local preference. And it's a way that we get to when we're looking at BGP from a high scale point of view, and you want the provider to implement a policy, but they don't want to have to maintain that operationally for you. So they say, here's my standard set of communities. Based on how you signal me, I'm going to change the local preference of the route as it comes inbound, which means that ultimately it changes my path selection for data outbound. And we'll see that's the really key point to understand about path selection here, is that an inbound policy change affects outbound traffic. And likewise, an outbound policy change affects inbound traffic. So these two here in general, weight and local preference, you would set them inbound in order to affect outbound traffic flows. We then have the locally originated routes. These are the ones that we're actually injecting with the network statement, with an aggregate address, with redistribution. We would set these weights to be higher in order to prefer our local originations over somebody else. But assuming you're not actually originating the route, next selection is going to be to look at the AS path. So the shorter length is going to be preferred. Typically, this is the most common way to influence inbound traffic flows, is to set AS path prepending out. So if you look through the internet table and you see anybody's AS who's listed multiple times, it means that they're doing prepending or they're adding additional ASs to the path in order for that to be the less preferred way. Okay, then we have the origin code. We talked about this a little bit with redistribution. And the network statement, when you originate the route with the network statement, you use the status code of I for IGP origin. If you redistribute it, you have the incomplete origin code, which is a question mark. The one in the middle, EGP, you normally don't see this because this means the actual protocol EGP, which was the precursor to BGP. So the code doesn't even support it anymore. If you say router EGP, it doesn't have the feature in there. But technically, you could modify the origin code to be EGP in order to influence the path selection one way versus another. Okay, then we have the multi-exit discriminator. Now, the MED we're going to come back to in much more detail later because there's a lot of other exceptions to how this works. Now, in general, a smaller value for MED should be preferred. But the thing is that by default, this is only checked when we're peering to the same provider multiple times. So let's say, for example, that I have two peerings to AT&T or I have two peerings to Level 3. When I advertise routes to them and they advertise routes to me, I'm going to see the same AS path for all of them because they have the same view of the table. Okay, this means that if I want to affect my path selection inbound, I can set this attribute out to them to say prefer one path versus the other when you actually return the traffic. But the thing is that the MED normally is an indication of your internal IGP metric, So it's a way for you to signal your provider that this is my best internal path to the destination. So when you do the network statement from an IGP route, it automatically copies the med in order to try to automatically do this. But we'll see that there's a lot of exceptions to how this works. And in most cases, you'll see on the internet that med is not used, with exceptions of internet exchanges. Because in general, the decision process is just too complicated that you could set the med in one direction and you think it's going to do one thing and it ends up to do the opposite. So in a lot of other cases, there's better ways to influence path selection versus using the med, or instead of using the med. Okay, we then have external paths over internal paths. We talked about this before when we talked about administrative distance, but in this particular case, it's not a choice of distance 200 for IBGP versus distance 200 for eBGP. The logic here is that if you are learning the route from an external peer and an internal peer, it's not your route. Because if it's coming from eBGP, somebody else originated it. So the idea here is to route out of the AS as opposed to routing into the AS, or again, the difference between hot potato versus cold potato routing. So try to find the closest egress path to an eBGP neighbor over routing through your most optimal internal path, which means that you are transiting somebody else's traffic. Okay, then we have the IGP metric to the next hop. If this is equal, then we can start to do multipathing. Now, there is also a hidden command that says BGP best path AS path multipath relax. This we're going to come back to later and talk about how multipathing works a little bit differently in BGP versus some of the other protocols, because normally it has a strict requirement that it says the AS path has to be the same length in order to do multipathing with BGP. But in general, once we look at if I have equal routes out to the edge routers, then I can do multipathing to both of them. So in other words, this is your internal path to the egress router. So your IGP metric to the edge of your network. Once we get past this point, then we get into the tiebreakers. So things like what's the oldest route, what's the lowest router ID, what is the shorter cluster list length, if we are a route reflector, and then what is the lowest neighbor address. Now, most of these we don't really care about, because if we're influencing path selection, we're always going to change some attribute that is going to override these. So you could theoretically change your router ID to be higher or lower in order to affect path selection, but there's much easier ways to do it. You use local preference, or you use AS path. So technically, you could get a question that says, don't use local preference, AS path, med, origin, blah, 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 and it would get you all the way down into the tiebreakers. And then, yes, technically, you could change the router ID. You could change your IP on the interface to say who's the lowest neighbor, and then this would affect path selection. But ultimately, that's not what they're trying to do with these values. They're just trying to say we must select one best path at the end of the day, even if we're doing multipathing. If you do multipath, you still only select one, and you can only advertise one. So they're just saying we have to have some decision as a last-ditch effort in order to say A is best over B, and then A is the one that I'm actually going to advertise to other neighbors. Now, there are some other exceptions that we'll come back to and talk about later. For example, like the AS path, you could say AS path ignore. For the multi-exit discriminator, there are a ton of exceptions. So we could say to always compare the med even if they're coming from different autonomous systems. We could say, if we are in confederation, compare the med between my confederation peers. I could say, if the value is null for med, assign it an infinite metric as opposed to assigning it a metric of 0, where the default is null equals 0 as opposed to null equals infinite. And we'll see why this is significant, because med is a non-transitive attribute, which means that if I signal med to you, when you advertise it onto an eBGP neighbor, the value gets stripped. And the value gets stripped to null, the value does not get stripped to 0. There's a technical difference when you look at the actual packet update. Okay, then we have BGP deterministic med, which changes the order of the selection inside when we're actually comparing the med between different paths. A lot of these, like I mentioned, we're going to come back to in later detail, because there's very specific exceptions to how med is actually used. Okay, we could also technically ignore the IGP metric, which is introduced in iOS ccie 3.4. I'm not 100% sure if this is in the regular iOS code trains yet. And then you could also tell it not to compare the router IDs. Okay, there's a couple questions here. Isn't the first best path selection to check if the next hop is reachable? It's technically not a condition of best path selection. It's to say whether the route is valid or not. And if the route is not valid, then you don't run path selection on it. So again, that goes back to those prerequisites of what do we need to even have first in order to think about doing the path selection, which is that we must have a route to the next hop. The synchronization rule must be met or disabled. The AS path can't contain our local AS unless we allow it in, and the neighbor that we're learning it from has to be the same AS as what we actually have them configured with the neighbor statement towards them. Okay, so let's talk about now how would you actually manipulate the path selection. And this is a very key important point to understand because the process of affecting outbound routing is different than the process of affecting inbound routing. And as I mentioned before, you have ultimate control over how traffic leaves your autonomous system, but you can only attempt to influence how it returns. Now, in most cases, it's kind of like a gentleman's agreement that with BGP, I am supposed to honor your attributes. I'm not supposed to rewrite them. But there's nothing to say that I technically can't. So you may signal me with AS path prepending, and I override it with local preference. Or you signal me with a specific community value, and then I just delete it from the path. So there's no technical reason to say why you can't delete other one's attributes. It's just that it's understood it's like bad etiquette to do that on the internet. So again, here the outbound routing policy affects the inbound traffic. The inbound policy then affects the outbound traffic. It's always the opposite direction. Now, regardless of the attributes, keep in mind that the longest match always wins. This is both for inbound and outbound. So if there's some reason that we want to override a policy, we can always do it by leaking more specific routes. So if I have 2/24s and they're both aggregates, and I want to affect traffic for just a portion of it, I could leak you a /28, pick some addresses out of that pool, and then say, I give you the 28 only this direction, then you're going to have to return the traffic back in that way. So again, we saw an example of that with the conditional route advertisement, that if I advertise you the route in this direction but not the other one, then you only have one path. The best path selection doesn't really come into play. But under normal circumstances, assuming that you have equal longest matches and you have diverse paths, then you're going to start to look at the attributes. Now, in order to influence our outbound path selection, so how traffic leaves the network, we're going to generally set weight and local preference inbound. So here the inbound policy is affecting the outbound traffic. So take, for example, our high-level diagram here. Let's say that we're looking at the network from the perspective of AS100. So this is where we live. This is where we're trying to make our path selection changes. And we have multiple peers that are going to AS200. We peer to router 3, we peer to router 5, we have a peering in this direction. So there's multiple ways that traffic can leave our autonomous system. Let's say in this case, we want traffic to prefer to leave via router 3. So this means that when the packets go outbound, we want them to go this way. So we have outbound traffic, which means we need to change our inbound policy. So there's a policy applied in 3 different points here, inbound. Now, depending on which particular attribute we're using, the difference between the two of these is going to be, does it affect everyone in the AS or does it just affect me? So again, weight is only a locally significant value. That's why it's kind of bad practice to use it. Because we want everyone to make the same decision. We may not want just me to say go that way and then everyone else goes a different direction. But the point being, they give you that flexibility in BGP, that you can make the policy locally significant or you could make it globally significant to everyone in your AS. Now, if we were to use local preference, the default value is normally 100. So you can change the default value, but in most cases, the default local preference will be 100. So if I wanted to prefer my traffic to leave via router 3, I have a couple different options. I could set the local preference to be higher as I receive this update, or I could set the local preference to be lower as I receive the other updates. you assume routers 7 and 6 are peering as well, either of these changes would have the same effect. Because the local preference value is significant to everyone, if I basically poison the local preference by setting it lower, that means that will not be my best path, and then I will not advertise it to the other neighbors. So again, keep in mind, as we talked about, the view of BGP will be different depending on who you are peering with and where you are in the topology. If you don't have a full IBGP mesh, not everyone's going to know all paths. You would only know the paths that the route reflector is selecting as best, or depending on how the sub-ASs are configured in confederation. But the idea is that since local preference affects everyone, you can set this inbound higher on the path that you want to prefer out, and normally everyone should honor that. So again, there are other ways besides using local preference to affect outbound traffic flows, but this is by far the easiest way. Then the opposite again is going to be for inbound path selection, for inbound traffic flows. So I want to say when traffic returns to me, how can I do that? I normally do that by using AS path prepending or by setting the med value out. So you set these values outbound and they are going to affect inbound traffic. So let's think about this in the other way. That we want to say when traffic returns, let's say to router 6's loopback, I want it to return via router 4 and go that way. This means I need to change my outbound policy. So the policy that 6 is advertising to 7, that 1 is advertising to 3, that 1 is advertising to 5, that 4 is advertising to 5. So in general, you need to take into account every ingress and egress path. Otherwise, you might set the policy on one portion of the network and you forgot to account for the other one, and then it doesn't have the end result that you want it to. So in this case, if we were to use AS path prepending, we would basically prepend out on every peering except the one that we want to prefer. So here our AS is 100, we would set 100, 100, 100 as 1 advertises the routes to 5 and as 1 advertises the routes to 3. Then likewise 6 would set 100, 100, 100 as they go out towards router 7, ultimately to try to get it to send the traffic this direction and then back in via router 4. Now again, when you're looking at this from a practical implementation and you're actually trying to do this on the internet, in order to check the policy, this is what the BGP route servers are for. Because when you look at an outbound policy, you can't locally check what is the actual end result of that. You need to go into someone else's network and look at what their view of your routes are back inbound. So again, there's a lot of different route servers that you could choose from. If you search for the BGP Looking Glass project, you can find a big list of them. But let's say, for example, that we were to go into routeviews.org, which again is the University of Oregon Internet Exchange. This is in US West Coast. And let's simply look at the show IP BGP. And let's pick any of these paths and look at how is it actually choosing one path versus the other. So let's just take the very first network for simplicity. We have 1000/24. So if we look at that particular route, let's say show IP BGP 1000/24, it says I have 31 possible routes to this prefix. The best route ended up to be number 22. Now, unfortunately, there's really no good way to ask the BGP table, why did you make the decision? You just have to manually go down the list and look at the weight values, look at the local preference values, and so on and so forth. But you might be able to look at who is the best path currently and then get some more information on it. So let's go down a little bit further and see which route is best. And it might be something obvious as to what it was, which here is the actual prefix here. It has an AS path length of 2, an origin of IGP, a mid of 6, and a local preference of 100. So let's look back at the table again. Well, you can see right off the bat what are some of the prefixes that probably would not be preferred. Those would most likely be the ones that have the higher AS paths. Because if we go back up a little bit here, Notice what was not changed is the local preference. This shows as a null value. This means it's the default of 100. The weighting is not set on any of these prefixes. It's defaulting to 0, so basically neither of those are taken in the decision process. Okay, then the next one mainly is going to be the AS path. So this one is ignored, this one is ignored, this one is ignored, and so on. So get rid of any of the ones that are the longer path, and then start to compare the attributes between the shorter paths. Now, assuming, and I don't actually know because we can't see the config here, we don't know if this router is actually configured to compare meds or not. One thing I can tell, though, is that it is not configured to set missing as worst, because if BGP best path med missing as worst was configured, what we would see here under the metric is some very large value. It's like 4 billion, whatever number, versus just a missing value. So again, as I mentioned here, there's a difference in null versus 0. Now inside the packet, I don't know actually how they signal it, but there is a numeric value that means null as opposed to a numeric value that means 0. And depending on what the router's code is, depending on how it's configured, it might choose 0 better than null, it might choose null better than 0. But also if we were to look through some of these paths, we could search for maybe paths that have multiple ASs in them in order for prepending. Now you could just look at these manually and see if any of them kind of stick out that show prepending happening. But we could also search through the AS path based on a regular expression, which specifically would be, and actually let me show this here real quick in the documentation, where this is documented for the regular expressions, because it is not self-explanatory at all where this is documented. So if you get to the configuration guides first, so we would, from the main page, we go to products, iOS, regular iOS, whatever the train is, configuration guides, now we're at this page. Okay, instead of in BGP, where it should logically be documented, it is actually hidden all the way at the end under terminal services, and then under the appendix for terminal services under regular expressions. Okay, what this is used for then is to search through patterns inside of the AS path and then search for certain characters. Now, the reason actually it's documented under terminal services is that regular expressions aren't specific to BGP. They're a general tool, and they were originally used in the analog modem chat scripts. So it's part of legacy terminal as opposed to BGP, but in our application, we're using them for BGP. So on this document, you can see what are the special characters and what do they specifically mean. And what I'm going to show here first is how do we match, and let's look at a couple just very basic searches. Let's say 1 AS in the path. This would be caret, which is to start the string, 0 through 9, which would be any particular number, 0 through 9, and then plus is one or more instance. So we're saying there has to be at least one number there, but there could be more, and then the string terminates, which would be a $sign. So if we said this, if we said show IPBGP regex caret dollar or caret, whoops. Let me try one of the other routers. Basically, this router has way too many views, so it is just chugging along. Let's take one of Comcast's. And you can notice they'll tell you that due to high CPU utilization, ping and trace route's not going to be a reliable indication of their core route, but it at least does show you their view. So if we said show IPBGP regex caret open brackets 0 through 9, close brackets plus $sign, this should show us any, and now of course the authorizations failed, this should show us anything that has a 1 AS path length. Actually, the reason why they deauthorize this is there's certain regexes that you can cause the router to do a recursion loop, and you can actually crash the router. We had kind of an interesting write-up on it. It was reloading the router from unprivileged exec mode, that there's certain strings you could send it that it gets into a recursive loop and then it just crashes. So let me try routeviews.org again. Okay, there we go. So this is saying somebody who has just one AS in the path. Okay, then you could say look for someone who is originating a particular prefix. Like let's say, for example, AS701, which I believe is AT&T. If we said show IPBGP regex underscore 701 $, that would say look at the routes that came from that AS. Okay, so this is the space that they own. The opposite of that would be if you say caret 701 underscore, this would be the routes that are coming directly from that peer. So they're peering directly with this, and let me actually double check this. Actually, no, AS701 is UUNet, which is now Verizon. 7018 is AT&T. But what I'm looking for here is I want to see paths that have more than one of the same AS in the path. So the search would be to find the AS number and then to reiterate it one or more times, which would basically be something like this. We would say show IPBGP regex, and then somewhere in the path, it could be in the beginning, it could be at the end, but somewhere in the path there's going to be an individual AS, so 0 through 9, plus, that's the actual AS. Then we're closing it, and we're saying that, actually I need to say close parentheses afterwards, and then we're going to say that there is, we need to reiterate that, which would be /1. And I want to say that this is going to show us any AS that is prepended. Command authorization failed. You can see some of these complicated searches, they don't let you run anymore because, like I said, you can cause a recursion error. But we'll try this out later when we actually look at the AS path lengths. If you see anyone who has their AS prepended over and over and over, like let's say, let's try it a little bit simpler. Let's say somewhere in the path is 7018, 7018. Which again, this one is AT&T. So for whatever this particular prefix is, they're trying to say that whoever is 3257, they don't want their traffic to return for this particular prefix in order to get there. And again, it's because they're applying this as an outbound policy. So the outbound policy is then affecting the inbound traffic. When I make my best path selection, I will not prefer one that has the longer AS path length. So the result then is the outbound policy affects the inbound return flows. Now we'll also talk a little bit about later how does multipath load balancing work, because it works differently for internal BGP versus external BGP, or you can turn it on for both of them. But the real key point to remember about this, even if you do multipath, you still only have one best route technically. Even though multiples can go into the RIB and the FIB, you only have one best route and you only advertise that particular path. Now there are more exceptions to this even beyond this. Like we could say BGP best external, which is going to say take your best route but also advertise your external best route, which is going to be used for fast failover. Some of those other exceptions we'll talk about later. But in general, there's only really 4 rules that we care about. It's going to be weight and local preference would be set inbound to affect outbound traffic, and AS path and med would be set outbound in order to affect inbound traffic. Okay, there's a couple questions. If you have 2 internet edge routers with different ISPs, what is the best way to load balance outbound and inbound? That's a very difficult case actually. Normally you can't, because typically the AS path length is going to be different, and then your internal metrics to them might be different. So we'll talk about that a little bit later. If you do want to do multipathing, you could turn on AS path relax and then just kind of send the traffic wherever. But what might be even a simpler solution is not to use BGP for the path selection. You could just do 2 default routes outbound and then originate the defaults into your IGP and just get the traffic up to the edge, because you can do load balancing on a default route. Now remember also, just because you are using a default route out doesn't mean that you can't influence your traffic flows back inbound. So I can advertise you my specific prefixes, but only accept a default from you if my topology view is not diverse. Because if I have 2 ISPs, if I have AT&T and Level 3, I really don't need a full view. I may want to say, take AT&T's directly connected customers, take Level 3's connected customers, and they probably would have the best routes to them. So using their internal transit to get to who they're connected to, but beyond that, I'll just default. Because again, the issue with this is the scale of the table. That when you look at the route servers and show IP BGP summary, not only are there over 500,000 routes, or I should say 500,000 prefixes, you have multiple paths in order to get there. So this one has specifically 523,469 networks, but then it's got 15 million routes in order to get there. So before you can even forward any traffic, we have to run through the list of 15 million routes, run the path selection on each of them, and then present those to the RIB, which can ultimately feed those to the FIB. So any way that we can cut down on this number of routes, but still make at least some sort of an intelligent decision, then you're probably going to be better off doing that. Because it does take a lot of hardware resources, not only to take the table, but then to actually forward efficiently once you have the table actually known. There's a question, is there an easy way to learn the order of the selection process or deduce it from the CLI? As far as I know, no. So unfortunately, that document that we have there is outside of the scope of the I believe what you would have access to in the exam, and the CLI doesn't tell you what the order is. So unfortunately it's just one of those things I would recommend to memorize, which is far and few between that I would recommend that you guys memorize stuff, honestly. But unfortunately, this is one of them.